Here we have this problem here. It says the dry and the wet bulb temperatures of atmospheric air at 1 bar. So the pressure of atmospheric air is given, and the pressure is basically the partial pressure of dry air plus partial pressure of water vapor. Now the sum of these two pressures is 1 bar. That is what the question mentions. And it says the dry bulb and the wet bulb temperatures are measured using a sling psychrometer. So you can use, there are several devices for measuring these temperatures, right? The wet bulb and the dry bulb temperatures. And we're using a sling psychrometer for measuring them. You can Google up and see how this looks. It's a pretty small, handy device, portable device. And it gives us the dry bulb temperature as 25 degrees Celsius and the wet bulb temperature as 15 degrees Celsius. Okay. Now using this information, we need to calculate humidity ratio, which is nothing but omega, and relative humidity, which is phi. Okay. Now for you to make use of this information, we need to remember that the dry bulb temperature is nothing but the temperature of the moist air, right? The ordinary temperature of moist air. And this is something that we will need in the calculation of omega. The other thing is the wet bulb temperature. And as we just discussed, the wet bulb temperature is equal to the adiabatic saturation temperature, all right, at atmospheric pressure. So we have the adiabatic saturation temperature as well. We have the temperature of the moist air, and using these two temperatures, we will be able to calculate omega. So let's make use of the formula. So this is the formula that allows us to calculate omega. This is there in the formula sheet, but you should know what each of these terms are so that you can calculate that. Okay. So we need a couple of enthalpies in here, and the only other unknown apart from the enthalpies which you can get from the tables is this omega prime. Omega prime is basically the omega at the exit, right? And we said omega at the exit is going to be saturated vapor, and we make it saturated vapor by adding up more and more, let's say, water vapor as it passes through this the liquid containing container, right? Or as it passes through this wet wick. So basically, the omega at the exit should be greater than the omega at the inlet, right? We will calculate both of these. So omega, simply omega is omega at the inlet, and omega prime is omega at the exit. Okay. So for us to calculate this, we need to first calculate omega at the exit. And omega at the exit is simply given by this formula, where the pressure or the partial pressure of water vapor is equal to P sat at the adiabatic saturation temperature. Now, why is it adiabatic saturation temperature? Well, simply because the moist air comes out as saturated vapor at the adiabatic saturation temperature. Okay. So now we can start by calculating this. So the adiabatic saturation temperature is given as 15 degrees Celsius here. That's the wet bulb temperature. So we calculate omega prime by plugging these numbers. So this 0.01705 is nothing but the P sat at 15 degrees Celsius, right? So you put that number in, divided by 1 minus the same number. Where do we get the 1 from? Well, it's the pressure of the mixture. So it was given as 1 bar. Okay, so P by 1 minus P times 0.622, and this is the quantity of water vapor at the exit, or quantity of water vapor per unit mass of dry air. Now we want to do the same thing for omega, right? We want actually omega. We are not so interested in omega prime. The only reason we got omega prime is because we need that for calculating omega. So here let's look at what are the different terms. This one is corresponding to an enthalpy of dry air, okay? Dry air at adiabatic saturation temperature, or the wet bulb temperature. This one corresponds to the enthalpy of dry air at the dry bulb temperature, or simply the temperature, plus omega prime times the Hg. Hg corresponds to the enthalpy of saturated vapor, right? Water behaving like a saturated vapor at adiabatic saturation temperature, or the wet bulb temperature, minus enthalpy of saturated liquid at the adiabatic saturation temperature. Why do we have HF here? Well, as we sort of recall, if you go back here, in this, the water is entering as compressed liquid, or you could say saturated liquid. And we know that for compressed liquid, the enthalpy is simply equal to HF at the temperature of interest, right? So that's why we have, when we're looking at this quantity right here, it is HF at the adiabatic saturation temperature, which is the temperature of the water that you're sending in, okay? Now coming back to this, the other two terms are simply Hg. Hg is the enthalpy of saturated vapor at the temperature it enters, so the dry bulb temperature, minus HF again at the adiabatic saturation temperature or the wet bulb temperature. Okay, so now it's very easy to get all of these enthalpies from the property table, right? Once you know which temperature you're looking for, and once you do that, I mean, you can put all these numbers here. Here instead of I mean, there are two ways you could, here you have H delta H for essentially air. You could get it from the ideal gas tables, or you could just use Cp delta T, right? So both are perfectly fine as long as we're dealing with psychrometric. So here I'm using Cp delta T plus omega prime times enthalpy of vapor at saturated adiabatic saturation temperature minus the enthalpy of saturated liquid at adiabatic saturation temperature. Okay, so these both are at 15 degrees Celsius. Then this quantity right here at the bottom is at 25 degrees Celsius, right? The dry bulb temperature. And this one again is at 15 degrees Celsius, the wet bulb temperature. So this is the omega when you plug in the numbers, and it comes out to be 0.00665. And as expected, omega is smaller than omega prime. In fact, much smaller than omega prime. Okay, so that's basically the humidity ratio done. Any questions there?
Yes, doctor. I didn't get it how you calculate omega prime when you use BG
Mm-hmm.
TAS. I get the TAS
Mm-hmm.
and the B. It's 1 bar.
Yeah.
But what's BG?
Okay, so basically PG is essentially the partial pressure of water vapor at the exit. So PG basically is the partial pressure for saturated vapor at the adiabatic saturation temperature. Is that clear? And this equation is,
Yeah,
by the way, in the formula sheet. Yeah.
it's
Okay.
pressure over a pressure, right?
Yeah, yeah. So this, let me just write omega prime here. So omega prime is simply 0.622 times pressure, let's say pressure at state 2 by P minus PV at state 2. This PV at state 2 or at the exit is equal to the P sat at adiabatic saturation temperature or P sat at the wet bulb temperature, right? So PSAT or PG is essentially the same thing. It corresponds to the saturation pressure at the adiabatic saturation temperature. We write it PG because it comes from this HGHF thing, right? We want to refer to the pressure of the saturated vapor. But I mean, we know that saturated vapor, saturated liquid, both of them are exactly at the same pressure within the dome. So yep, that's essentially what it is. It's equal to the saturation pressure at the temperature that we're looking at.
Okay, thank you.
All right, so that's the first part done. That's omega done. Now we also need to get the relative humidity. Now we know the formula for relative humidity. It's PV by PG, right? And this PV is the partial pressure of water vapor at the inlet, right? And PG is the PSAT at the temperature of interest, right? Which is in this case the dry bulb temperature of 25 degrees Celsius. Now we need to figure out a way of getting PV. Now it turns out we have omega, and omega by definition is 0.622 times PV by P minus PV. Okay, so we have omega at state 1, which is simply written as omega. So using this, we can calculate PV1, and then we can substitute this PV1 back into this equation for relative humidity. All right, and there's again there's a formula for that, and this is the formula that allows us to do so. So this relative humidity is written in terms of omega times Psat at the temperature of interest. Remember, this one is uh, Psat at 25 degrees Celsius. Okay, whereas here we were looking at Psat at the adiabatic saturation temperature of 15 degrees Celsius. Why are we looking at different temperatures? Well, we are talking about two different states. Here we were looking at omega at the exit. Okay, at the exit, we expect the air to be saturated vapor, and it comes out to be at the adiabatic saturation temperature. Whereas this one is the omega. This is the phi that we want to measure at the inlet, or the phi of moisture per se, right? And therefore, it needs to be measured at the temperature of the moisture, which is 25 degrees Celsius. Okay, so omega is something that we already calculated in here, and it's just a matter of plugging in those numbers here. And when you do so, it comes up to be 33.38%. All right, so using simply the dry bulb temperature, which is the temperature that we see everywhere, and the wet bulb temperature, which you can measure by putting a wet cotton cloth on top of the thermocouple. By only measuring these two temperatures, we will be able to say a lot about the amount of moisture content within the air around us, right? Omega and phi. So this is one way of doing that. There are also some electronic devices or electronic sensors which allow us to measure the quantity of water vapor and thereby use it to come up with these numbers. Okay, any question here?
Doctor, is this equation formula sheet?
Yes, this equation is there in the formula sheet. The only thing is you should know how to use it. So see which temperatures we are looking for, and you should be able to solve it, inshallah. All right. So then let's move forward. So we have been talking about a lot of these temperatures. So I just wanted to give you an idea about what sort of temperatures do we have around us. So this is the weather forecast for today. Now it's probably around 29 degrees Celsius. So 29 degrees Celsius is basically the dry bulb temperature. Okay, this is the temperature, the normal temperature of the air around us. Now in the morning when I picked up these numbers, the humidity was given as 65%. So this 65% is nothing but the relative humidity, right? And it was, I mean, the temperature was sort of low. So for the same amount of moisture level, the humidity you could say was slightly on the higher side. I also looked up the dew point temperature. Now again, this is at a different time. This was late night yesterday, maybe around 1 a.m. So the humidity was even higher. It was about 83%. So this again is relative humidity. And at this condition, the dew point temperature was 20 degrees Celsius. So these are all numbers which are available on the internet, right? So you can look at these numbers, and essentially from the dew point temperature, what you can see is that if you have at this time when the relative humidity was 83% and the dew point was 20 degrees Celsius. So if you have some let's say if you have a cold drink or a cold glass of water whose temperature is below the dew point temperature, you will see water droplets forming on the surface of the container. Or you could say that if the air temperature, if the dry bulb temperature at night, if it goes below 20 degrees Celsius, then you will see water droplets on your windshield of your car, right? So essentially, this is how all these temperatures are around us, and they sort of are pretty useful quantities. Okay, so I've also put up a slide here to so that you can have all the formulas that we have used till now in one place, and it's easy for you to do the homework. Okay. All right. Any questions? Anything else that is not so clear, or you want more explanation about? Yes, Sami.
Yes, doctor. When I see water condensing on a glass or on a soda,
Mhm.
does that mean that the relative humidity around it is 100%, right?
Yes, yes,
But
that's
but
right.
not the relative humidity of the atmosphere of like the Dahran.
That's true.
Okay, okay.
Yes. So basically, uh, the part of the water vapor that gets condensed is the water vapor or the air that is the moisture that is just surrounding the let's say the glass of cold water, right? If you measure right there, then yes, some of it gets condensed, and then the part that is getting condensed and the air around it is going to be at the saturated vapor state. But if I measure somewhere else a little bit away, then it's going to give whatever the relative humidity is, 83% or whatever it is. So yes, that's a very good point. Uh,
Again, doctor,
Abbas,
can you
yes,
explain it? Yeah, the same question, doctor. Can you explain it again?
sure. Let's go back to this and see. So here we said that this is the we notice this water getting condensed on surfaces, right? So The water that got condensed here is basically the water vapor from the air that was touching the surface of this glass, right? Or being touching the surface of your car windshield and so on. So it is exactly that specific air which is very close and which is touching the glass surface that undergoes this process of initially going from its initial temperature to the dew point temperature and then going below the dew point temperature. If let's say the dew point temperature for for the amount of water vapor that you have in the in your room, let's say if the dew point temperature is 20 degrees Celsius, we know that the cold water temperature or the temperature of the glass is it's going to be lower than that, right? It's probably maybe 10 or 15 degrees Celsius. So since it's lower than 20 degrees Celsius, the air that is nearby undergoes condensation and it goes through this process, whereas you can see water droplets and you can the air nearby, the part of the air which sort of got condensed, it's going to be saturated vapor with 100% relative humidity. But this is only the air that is touching the cold surface or very close to the cold surface. If I'm looking at some point farther away, maybe even here, right, which is this air is not even touching the cold surface. For this air, it is not at relative humidity of 100%. It is relative humidity whatever is there in the general air, maybe 60%, maybe 70%. But only the air here right on the surface is going to have 100% relative humidity because it goes through this path, right? Initially reduction temperature till the dew point and then below the dew point with some part condensing, the remaining continuing to stay as vapor but as saturated vapor. Okay.
Okay, because it's touching the system, it's we say 100%, but because it's far away, as the previous example,
Mhm.
83%, right?
Yeah, so what we normally measure is the air conditions a little bit far away from any given surface. So even if you look at the temperature, right, the temperature of the air which is touching the glass, it goes down, right? It is smaller than the temperature of the air anywhere else. So it's simply because of reduction in temperature when it touches this glass. So which is causing this condensation to happen. On the
Okay.
other hand, I mean, you can also have dew. Typically, dew is observed later in the night. So at night, sometimes the temperature goes below the dew point temperature, right? So for the amount of water vapor that we have in the air, let's say again, the dew point temperature, sometimes in on humid days, the dew point temperature could be as high as 25. But during the evening, the dry bulb temperature can become maybe 20 degrees Celsius. So at this point, the all the water vapor in the air or some part of it, it starts to condense, right? And this shows up on any surface you can see. So it shows up on leaves. I mean, when we walk out, so our glasses get fogged up, right? That's again is because this exact phenomena is happening. Some amount of water vapor that got in touch is getting condensed. So this is a very common phenomena and something that we sort of notice around us. All right, so we have a couple more minutes. I'll just introduce you to the concept of the psychrometric chart. I'll provide more details on the psychrometric chart on the recorded lecture that I'll post on Thursday. Okay. Remember, the psychrometric chart is really important. So when we have the pop quiz on Sunday, there will be one question on how to use the psychrometric chart, right? So make sure
Your
you
voice is
understand. Is my voice clear now?
Yes, it is clear.
Okay.
clear.
Yeah, it is clear.
All right. So I will mention about the pop quiz again a little bit later, but make sure you look through the psychrometric chart carefully. So psychrometric chart is nothing but sort of a chart indicating the properties of air water vapor mixture or giving us moisture properties. And this is drawn for an atmospheric pressure of 1, right? And this is drawn in such a way that it becomes very easy for us to understand what processes are happening when you're dealing with air conditioning applications, right? So if it's cooling, humidification, heating, all of these can be easily shown on the psychrometric chart. So here on the psychrometric chart, the y-axis is the humidity ratio omega, okay? The x-axis is the dry bulb temperature. And then we have a lot of these other axes showing the different parameters. So you can see all of this one. This line corresponds to a relative humidity of 10%. This line 50%, and this one line is saturated line. So this is 400%. Same way, these parallel lines that we see here, these correspond to different enthalpies, and then you have similar parallel lines giving the wet bulb temperature. We're going to go through each one of these in detail to see how you can identify. Okay, so let's say we have a certain point, we fixed a certain state here by knowing two independent intensive properties, right? So if you want to measure its dry bulb temperature, then you just draw a vertical line straight downwards, and this one gives you the dry bulb temperature. Same way, if you want to measure its, let's say, humidity ratio, then you just draw a horizontal line straight that meets this y-axis, and that point exactly is going to give you the humidity ratio. Okay. Now, the excellent point about this psychrometric chart is that, let's say you were given the dry bulb temperature and the wet bulb temperature. Okay, and through this you are able to locate the point. So you have the dry bulb temperature right here. So you use this as one axis, and the wet bulb temperature is on this axis of 100% saturated line. So there are different, lines parallel to this constant enthalpy line, which stand for different wet bulb temperatures. So using these two, let's say I'm able to fix the state. Once I have the state, then using the psychrometric chart, I will be able to find all other properties such as omega, relative humidity, and everything else. We don't have to go through the calculation that we just described, right? It is not to say that you should not know how to do the calculation, because sometimes in the exam we say, we give you a situation where you need to calculate omega and phi, and you are not allowed to use the chart, okay? Because we want to test on the theory part. And there will be another question or similar question where we ask you to specifically use the chart. So you should not use the chart everywhere. Just use the chart where the question asks you to do it, right? So anyway, so this is for the humidity ratio. Same way, you can go and look at other different temperatures. So for example, the dew point temperature. If you look at the definition of the dew point temperature, well, the dew point temperature is basically the state where the moisture that you have initially, it becomes saturated. So you need to keep cooling it down. So keep cooling it down meaning you go to the left on the dry bulb temperature scale, while keeping omega same, right? The amount of water vapor should remain exactly the same. So you keep going towards the left, and the point where you reach 100% saturation, well, that is a point that corresponds to the dew point temperature. So I just draw a horizontal line to the left, and then draw a vertical line bottom to get the dew point temperature. So again, just to look at it from a different perspective, you have the temperature volume specific volume diagram. We said if you're looking on a constant pressure line, which corresponds to constant PV corresponds to constant omega, you start cooling it down from state 1, and you keep cooling it down till it reaches saturated vapor state, which is let's say state 2, phi is 100%, right? So the temperature at state 2 is the dew point temperature, and that's exactly how we achieve the dew point temperature from the psychrometric chart. So you cool it down while keeping omega same. When you reach 100% saturated state, then go down. That's exactly how you get the dew point temperature from the chart.